Hello! Welcome to today's mechanics tutorial video, where I'm going to be showing you how to draw force diagrams, which are useful things to draw when doing calculations involving forces. However, before we begin, I must give you a disclaimer, as I'm approaching this video from the point of view of a mathematician, and therefore the level of detail I'm including here will be in line with the idea of force diagrams being used as a tool to help us with calculations. Whereas, for people studying a physics qualification, it's likely that more detail would be needed than what is being shown here, to fully ensure any force diagrams are reflecting all of the necessary physics principles and properties of the given scenario, in line with the marking criteria for those types of qualifications. Okay, with that out of the way, let's explain why we even care about force diagrams in the first place though. Well, I've already given a clue that they're being used as tools to help with calculations, but how are they helpful in that way? Well, one of the main reasons they're helpful is that they help us condense the information from a wordy scenario into the key bits of information we need in order to do the calculations we're going to be doing with them. Therefore, in many ways, it could be viewed that the force diagram is summarizing the situation in a nice, easy way for us. Another key point though is, as part of doing that, it therefore helps break the question down into those key bits of information, so it's more clear about where the different parts of the calculations we're going to be doing are going to be coming from. But then there's an extra bit of usefulness that comes from them, which is, as part of breaking the question down, it helps us avoid silly mistakes, because it's compartmentalizing the various parts of the question, and therefore meaning we can just focus on those little parts as we're doing them, meaning we're more likely to avoid silly mistakes. And what should we do to actually draw the force diagram? Well, as we're just using the force diagram as a tool to help us with calculations, one of the first things we want to bear in mind is that we don't want to spend any more time than is actually necessary drawing the force diagram in the first place. One of the first ways you can deal with this is by not including any unnecessary extra detail, trying to make your picture a super pretty one that's a picture-perfect representation of the scenario. And instead, the most easy thing you can do is to represent every object you're trying to do a force diagram for as either a box or a circle. Doing this gives you the added benefit of A, not wasting time, while also providing you with the necessary room to add extra labels if there's more than one object you're having to do a force diagram for, so you can tell the two different objects apart. Let's say in one scenario, one of the objects you're dealing with is a car and the other is a trailer. Well, by drawing it as a box or a circle, you've got room to write that label inside the object. Or even if you have something more simple, like just the different objects are referred to as letters, object A and object B, well again you can represent that very nice and neatly inside your box or circle. Arguably the box has a few more advantages than the circle, just because a box has more room to be including more forces around the outside of it, rather than the more compressed shape of a circle. The next thing to bear in mind is that any forces you draw on the force diagram are represented by arrows, with the arrows going in the direction that the force is acting in. Therefore, we could have a box, and then we could have an arrow going to the left if there is a force acting to the left. Or alternatively, you could have a box, and then an arrow going to the left into the box, towards the box. In physics, they care about the difference and distinction between these two different scenarios, but for the point of view of maths, we really don't care which of these two scenarios you draw, as either of them are enough to indicate that there is a force going to the left, which is all you really need to know for the purposes of your force diagram. However, it is worth noting that your arrows representing your forces should be connected to the object you're doing the force diagram for. They shouldn't just be floating in space, unattached to the object. With that in mind though, what happens if we want to include other bits of information on the force diagram, things such as acceleration or velocity? Well, we could still represent those by arrows, but to avoid them being confused with the arrows representing the forces, we'll have the arrows representing acceleration or velocity as arrows not connected to the box. Going one step further, some people like to draw the arrows for acceleration or velocity as double arrows, because again that helps add that extra little bit of distinction between the arrows drawn for the forces and the arrows drawn for acceleration or velocity. So I'm talking about something like this. Let's say we have a box representing our object. We could have various arrows coming in or out of the object to represent the force arrows. But then if we want to have an arrow indicating that the object is accelerating to the left, we could have the arrow up here pointing to the left but not attached to the box therefore, and we could make it a double arrow. And therefore you could also include the number representing the acceleration and the units, because all these things together make it clear that it's not a force, it's separate to all those other things included as part of the force diagram. The last thing to bear in mind is that if you know the mass of the object, we do like to label that on the force diagram as well, and again we represent that information just like the label for the object inside of the box representing that object. So that's a nice straightforward way of representing that information in a nice consistent way, so you always know where to find that bit of information when you go to look for it when doing the calculations. However, as today's video is not focused on calculations, therefore this is not something that's going to be playing such a vital role in today's video. However, in future videos you will see me do this a lot. So that's what should be included as part of the force diagram, but how are you meant to know what forces to draw on your force diagram? Well, to a certain extent, there are a lot of forces that a question might just directly tell you about, like for instance telling you that there's a 3 Newton force acting to the right, and therefore you know to draw an arrow with the number 3 attached to it going to the right. However, there are some forces you're expected to go into a question already having a basic understanding of, and therefore knowing whether you should or shouldn't be including them for a particular scenario. So let's talk about those forces now. The first and most famous one is probably gravity. However, the word gravity is quite a wide encompassing term, and it's more often used when describing the physics on a more cosmic scale, or talking about a force that's acting on objects that are outside the gravitational field of Earth. So instead, the term we're going to be using is the term weight, which is the name we give to the force caused by gravity acting on the mass of an object. We'll talk about how to calculate the weight of an object more in our next video, but for the moment just be aware that weight always acts downwards on an object, towards the Earth. The next important force you need to know about is called the normal reaction force. I'm going to try and give you a basic overview of it, just so you have enough information to know when you should or shouldn't be including it as part of your force diagrams. Like with all physics things though, there's always more detail you can go into when talking about these things. So what I'm going to say about the normal reaction force is that it could be viewed as the force that's caused whenever a solid object comes into contact with another solid object. The purpose of it is to basically stop one of the objects phasing through the other, and also alternatively stopping one of the objects compressing or crushing the other object. There is a clue in the name, it's called the normal reaction force, and the word normal in maths basically means something to do with 90 degrees, and so therefore the normal reaction force always happens 90 degrees to the surface of the object that's creating it. So that's something to bear in mind. Another force that ends up occurring in a number of scenarios that you have to deal with is tension. And tension is basically a force that occurs whenever you have an object being pulled by a string or a rod. String or rod being physics terms for what we call modelling assumptions, but this could also mean in the real world things like ropes or wires pulling objects as well, and that are attached to the object. Okay, those are 3 of the most common forces you'll like to come across in a lot of mechanics problems, but there are also some other important forces you'll need to deal with, things such as thrust, friction and air resistance, but we'll come across those more in future videos. Other things to bear in mind is because we're lazy in maths, we do like to not have to write more than we need to, and therefore the 3 main forces I've written here are often referred to sometimes by just a single letter. So weight is sometimes referred to as just W, the normal reaction force is sometimes just referred to by the letter capital R, and tension is sometimes referred to just by the capital letter T. That makes them a lot easier to label on your force diagram itself. Okay, with all that said, now we could actually get on with doing an example. So our example 1 that we're dealing with here is we got a short metal girder, which you don't really need to know what it is, except that we just realised it's an object that's being placed horizontally, so that the 2 ends of this object are lying on separate wooden blocks. So what they're sort of describing, if I was to draw more of a picture rather than a force diagram of what's going on, is we have 2 wooden blocks, and then something placed horizontally across between them, so the 2 ends of the object are lying on the 2 wooden blocks. So, what forces are going on? Well, let's draw a force diagram to show this. So I'm going to draw the object as a rectangle, because that keeps things nice and simple. The girder is an object that's probably going to have mass because pretty much all objects in the world do have mass, and therefore if it's got mass, gravity's acting on that mass, so therefore the object's got weight going down. And then the object is a solid object and it's coming into contact with another two solid objects, once over here and once over here. And every time a solid object comes into contact with another solid object, that means we know a normal reaction force must be occurring. As the surface of the wooden block is horizontal, then the normal reaction force must be happening 90 degrees to that from that wooden block, so therefore the reaction force is happening directly up. So therefore we've got a normal reaction force from the wooden block on the left, and we have another normal reaction force from the wooden block on the right. Basically every time there's a point of contact, that's where a normal reaction force will be occurring. Cool, so that's example 1 done. But what other details do we need to watch out for? Well, something to bear in mind is that you should only include forces in the force diagram that are directly having an impact on the object you're doing the force diagram for. What does that mean though? Well, let's take a look at an example to explain that. Let's say we've got 3 boxes stacked on top of each other on a flat horizontal table. So if I was to draw a quick picture for what that looks like so it's easier to describe it, we've got a box on top of another box on top of another box, something like this if you accept my terrible drawing. In part A we want to do a force diagram specifically for the box that's in the middle of the stack. And that is something to bear in mind because it might change exactly what forces we do. So therefore, let's talk about this. So I'm going to draw a box. I'm going to label it as the middle box so I'm aware which object I'm doing the force diagram for. Of course, we're aware that this object has a mass, so once again it's going to have weight acting downwards. We then also have, of course, the fact that the middle box is coming into contact with the box below it. So therefore the box below it is going to be providing a reaction force going up. If you want to be more specific, because there's a lot going on in this scenario, you then might want to start including more detailed labels. So I could write R and then brackets from the box below. And then we also realize that, wait a minute, there's another box coming into contact with that middle box because there's the box on top of it as well. Now there's a couple of different ways you could look at it. You could view it as another reaction force that the middle box is experiencing because it's feeling the box on top of it coming into contact with it. But in this case, the reaction force will be going downwards because it's feeling the box on top of it pressing down on it. However, alternatively, you could also realize that the size of this reaction force is being caused by the actual weight of the box that's on the top. That is what the middle box is feeling. It's feeling the weight of the box on top of it weighing down on top of it. So that's a thing you could do, is you could just label it as the weight of the box on top. Obviously, I'm having to label things with names at the moment, but once you know these things as numbers on a real force diagram as doing calculations, then you would just, instead of labeling the name, you would just write the number a lot of the time, because that's the bit you'd really be interested in order to do whatever it is you're doing with it afterwards. But then for part B, well, you've got to start being aware that you've got to be careful. If we're doing the forces acting on the box on the bottom, well, again, there's some similarities. So let's say bottom box. But then we once again, of course, have the weight going down. We have the reaction force, which is coming from the floor below it. But then we start having to be careful because people are very tempted to start having an extra label going down to then represent the weight of the box that's on top of the bottom box, the middle box basically. But then they might then have a third arrow sometimes representing the weight of the box that's on the very top of the pile. However, I would not do that. As I just mentioned before we started this example, you should only include the forces directly impacting the object you are doing a force diagram for. A good analogy for this is to imagine every object when you're doing a force diagram as a human with their eyes shut. You could feel if something was touching you, but you wouldn't necessarily know or see things away from you. So you could only feel the things directly coming into contact with you rather than things happening elsewhere in the room or the world around you. So therefore, I'm only going to do one extra arrow in addition to the weight arrow we already have, and then I'm also going to be very careful how I label it. I'm not going to label it as the weight of the box above, because it's more than that. It's in reality a combination of both of the weights of the object above it, but again, if you start overthinking that sort of thing, that's where you can end up falling into traps and making silly mistakes. So instead, I am going to just label it in a very generic way. I'm going to label it as the force exerted by the box above, because then that means it's quite a wide encompassing term that can then be used to adapt for whatever the size of the force needs to be to make all the calculations work in the way that they're meant to work. So as I said, something to be aware of, don't overcomplicate it, just think about the forces that are directly acting on the object you are doing a force diagram for. The numbers should then deal with everything by making things bigger or smaller as necessary to take account for other objects that are indirectly affecting your object. However, this does open the door to another issue that you need to bear in mind when doing force diagrams for scenarios that have multiple objects involved. One aspect is that you can draw individual force diagrams for the individual objects in the scenario. But in some scenarios where you have multiple objects all acting in the same way because they're connected to each other in some form, then it is in your interest to then treat all those multiple objects all together as one big object, rather than treating them separately. The advantage of doing this is it can help you simplify in your mind what's going on, and helps you avoid overcomplicating it and double accounting for things that you don't need to double account for when doing the various force diagrams that you would have to do for the individual objects. This therefore leads to the last bit of advice I want to give you, which is just to not overcomplicate things. With this mechanics stuff, it's very easy to start thinking in greater and greater detail, thinking about how different things can be affecting each other to the point where you're thinking about things on an atomic level. But that's just unnecessary for mechanics. Most of the things we're dealing with in mechanics are meant to be fairly intuitive and in line with your experiences of the world around you already. And although it's possible to start thinking about things in more and more detail, doing so will often lead to people including forces that shouldn't be there, or not including forces that should be there, or double accounting for forces that actually are there but are being counted for twice by accident. So therefore, do try to keep things simple where possible. And in fact, here's an example to illustrate this issue. We've got the scenario where we've got a parachutist that's deployed their parachute during a skydive. They're descending, which is basically a posh way for saying they're going down, and we need to draw a force diagram for the parachutist. For a start, here's a picture just so we can visualize what's going on. We've got the person attached to all the gear they need to have a parachute and the parachute itself. Now, it's all dependent on how complicated you want to make this stuff and what you do or don't want to include as part of the force diagram. The easiest thing in this scenario is to realize that all of these objects are traveling downwards together in the same way, and so therefore the easiest thing to do would be to do a force diagram that's for the parachutist and all their gear. So that is what we're going to start by doing. So therefore, doing this makes the scenario quite simple. There are actually only two main forces acting on this parachutist. There is the weight of the parachutist and all their gear acting down, and then going up, well, what's slowing them down, making sure they're not free falling, which I hope is what's happening? Well, ultimately there's a force called drag. You don't really need to know that because it's not a force we really deal with in the mechanics element of maths that much, but that is the official name for what's going on, and so therefore this is the force diagram done. This is by far the easiest way to represent the scenario. However, there is always more detail you could go into, and as you do that, that will change exactly what force diagram you draw when you're choosing to do that. However, while doing this, the more complicated you're making the scenario as you do this, therefore making it more likely that you'll make mistakes. For instance, one added layer of extra detail we could have given is we could have separated out the parachutist from their parachute itself. So therefore, we realize we're just going to be doing a force diagram for the parachutist and their harness. Once again, we're going to consider what forces are acting on them to do the force diagram, and the first thing we'll be aware of is the fact that they've got weight. This time though, there'll technically be slightly less weight because it will be just the weight of the person themselves and the weight of the harness itself, as well as their clothes, etc, etc. But what are the forces that are stopping them from free falling now? Well, there's still going to be a bit of drag or air resistance acting on them, so there's still going to be that force acting up. However, it's worth noting that air resistance is not the main thing directly slowing their descent. Although it's indirectly still doing it because the drag is acting on the parachute, which is then slowing the person down. As I already mentioned, you should only be including forces on your force diagram that are directly impacting the object you're doing the force diagram for. And so therefore, when we think about the scenario in more detail, we realise that what's slowing the person down when they're descending is the fact that their harness is connected to the ropes that are connected to the parachute. And therefore, these ropes are pulling up on the harness, and this force is what's slowing the person down. As it's a pulling force happening along strings or ropes, if you will, this is then harking back to what I said earlier and described as tension. So therefore, these are the other forces acting on the parachutist and their harness, if you're doing a force diagram for those objects only. As you can see, this has already made the scenario more complicated. And the thing is, you wouldn't have to just stop here. You could make this even more complicated if you want. What happens if you just want to do a force diagram for the person, not including their harness? Just the person and their clothes, nothing else. Once again, we're going to draw a block to represent the thing. In this case, our thing is a person. And once again, there's going to be the weight going down, but this time it's now just the weight of the person. But now, what's the force that's slowing the descent of the person? Well, it's ultimately the harness, and the harness is coming into contact with their body. And every time the harness is coming into contact with the body, the harness is a solid object, the person's body is hopefully a solid object too, and therefore every place the harness is coming into contact with the person's body, a reaction force is being created. And all of these reaction forces together are accumulating together to create that slowing down force that's required. Of course, we're secretly aware that these reaction forces are just being indirectly caused by the tension in the ropes attaching the harness to the parachute, and then the drag in the parachute is then indirectly causing that. But that's the whole point I'm trying to make with this. You could make the scenario more and more complicated by thinking about these things in more and more detail, by separating our objects from each other, but by far the easiest way to deal with this stuff is to just group things together as one big object, if there's no discernible difference between what those different objects are doing different to each other. Okay, and with all that said, that's all I wanted to cover today. Hopefully you found this video useful. Ultimately, we're going to be using force diagrams in a lot of future mechanics videos anyway, so you get more practice at seeing them in use and seeing me drawing them as part of bigger questions, but hopefully this was just an introduction to explain what you should be doing with them and what you should be drawing. Okay, see you in a future video. Goodbye.